Hello, my name is Rob Reynolds. Welcome to Business Calculus, Chapter 3, Section 7. And today we're going to put everything together and learn how to sketch a curve using all of the techniques that we've looked at so far. So remember, if the first derivative is less than 0, then it's decreasing. And here's another decreasing example. However, this is concave up, so that's the second derivative, and if it's concave up, it's greater than 0. But this says concave down, so the second derivative is less than 0. So over here, increasing means what? The first derivative is greater than 0, first derivative is greater than 0, and then concave up, second derivative is greater than 0, but the second derivative is less than 0 for concave down. So those are the four things that we're going to be looking at. Finding the derivative and setting it equal to 0, and then analyzing the graph by looking at the critical values and then setting up intervals, telling me whether the first derivative is positive or negative. Well, if the first derivative is positive and the second derivative is negative, then you know that the function is increasing and it's concave down. And in order for this to be a max, you'd have to find out that this was decreasing, because every time it moves from increasing to decreasing, then you've located a max. So we're going to learn how to fill out this chart and answer all of these questions about x-intercepts, domain is the left and right, range is bottom to top, whether there's any holes or discontinuity, if it's differentiable, relatives, maxes and mins, concavity up and down, inflection points, of course the second derivative, setting the denominator equal to 0 for vertical asymptotes, and then horizontal asymptotes. Horizontal asymptotes I talked a little bit about in the previous section. Just to review really quick, in section 3.6, we decided if the numerator is less than the denominator, then y equals 0. If the numerator is equal to the denominator, then we have this A over B relationship, which I'll show you an example. And then the last one is it's not horizontal at all, it's called oblique, and we divide. So some examples here is if the degree of the numerator is less than the degree of the denominator, since this 1 is less than 2, the horizontal asymptote would be at negative 2/3. Remember, just the coefficients out front. And if the degree of the numerator is equal to the degree of the denominator, then, this one is the negative 2/3. Let's try that again. If the numerator is less than the denominator, then y equals 0. So, oops, I bouched that. Let's try that again. That should have been the 0. And then if the degree of the numerator is greater than the degree of the denominator, you can actually do this long division. We're not going to do that, so I would just say there is no horizontal asymptote, it's actually oblique, and we could find what that oblique equation of that line is. It's not always a line, but it could be a line, by doing long division, and we'll skip that for now. Remember, when you're trying to sketch a curve, it's really important for you to look at your window setting. You might have to adjust your maxes and mins, because if this is what the graph is supposed to look like, and you're only looking at this part, you may think, well, I've located the max and that's it. But you could be zooming out and find out that there's actually a min and this thing goes up. One of the hints is y equals x cubed. You kind of know the general, hopefully you know the general shape of that. It finishes in the first and the third. So this doesn't really make sense. This really looks like a y equals negative x squared function here. So hopefully you know some general shapes of what the functions look like so you can help find them. So locate at relative extremes. This is the first derivative, and the inflection point is going to be the second derivative. So let's take a look at an example and see if we can fill out a chart. The first derivative for this is 3x squared plus 6x minus 9, and I could factor out a 3 and then factor some more and then set those factors equal to 0 to locate critical values, x plus 3, x minus 1. So possible, remember these are not necessarily, these are possible critical values, and I could even set up my intervals and start looking from negative infinity to negative 3, since this is a polynomial and I know it goes to negative infinity. 3 to 1, and then 1 to infinity. So then I would run my test. F prime is greater than 0, so it's increasing here. test something between -3 and 1 and find out it's less than 0, so it's decreasing. And then in this interval, f prime is greater than 0, so it's increasing. Again, you're welcome to use a chart here. So if it moves from increase to decrease, you've located a max at this -3, and you could plug that -3 back into the function to find that it's 32. And then decrease to increase, you locate a min. There's the minimum right here at 1, 0. So you're locating maxes and mins. You know, one thing, to find x-intercepts, you have to set the function equal to 0. So when you set x cubed plus 3x squared minus 9x plus 5 equal to 0, you could try to factor that grouping, but I don't think it does. Maybe you haven't seen synthetic division for a while, but you can synthetically divide by any one of those roots, a 1 or a -1. We should probably just we could try a -1. We could try a +1. I'll try a -5. You could try a +5. But synthetic division says bring down the first. We're looking for zeros, of course, down here. So you multiply. -5 times 1 is -5, and then add. Multiply again, and then add. And then multiply, and sure enough, you found a 0. So if this started out to be an x cubed, then this is a 1x squared minus 2x plus 1, and then you try to factor that some more, and of course it does. X minus 1, x minus 1. So you can see you've got a double root at x equals -1 and a single root at -5, and those are the 3 roots. And I know there's 3 roots because it's an x cubed function. So what does that mean? That the function crosses at -5 and then end at -1, and it's actually bouncing since there's a double root here, an x minus 1 quantity squared. I know it's bouncing here, and since it's positive, it's in the first, so it comes down here, it bounces, and then it kind of comes down again. So it kind of makes sense to have a max way up here at -3 and 32. So again, without a calculator, this is kind of all coming together. Well, let's go find the second derivative and then run some more tests. So the second derivative would be right here, the derivative of this, 6x plus 6. Set that equal to 0, and you get x equals -1. So I would run a test for -1. Now, instead of running a test, the book is going to ask you to fill in this chart. And to fill in this chart, kind of doing what I was doing before, we're going to go from -3 to 3. So then you look to see what's happening at 3. From -3 to -1, and you look to see what's happening at -1. From -1 to 1, another critical value. Look to see what's happening to 1, and then 1 to infinity. And you can go back here and say, well, at -3, we decided this was a 32 because of the previous slide. That gave us a 0, and it was second derivative is less negative, and then this was negative, so this is decreasing and concave down. Because the first derivative was negative as well, so it's decreasing. So you can go through and you kind of fill in this chart in. If this is negative and 0, this is a point of inflection. Negative, positive means decreasing and concave up. 0 and positive, you've located a relative min. So this is just try to help organize your thoughts. Positive means it's increasing and then concave up. And then with all this information, I think it would be pretty easy then to draw a picture like this. So you can see this is concave, well, there's the point of inflection. So this is concave down, and then over here is concave up. The hard part for this, for some of you, is just going to be finding the derivative, but not for this problem. You can see this problem is pretty straightforward. The first derivative is 4x cubed minus 36x squared plus 96x minus 64. Factor out of 4. And then if you continue factoring, we'll get x minus 1 and x minus 4 quantity squared. Again, you got a double root here at 4. So your critical values are 1 and 4. So then you test your intervals again. Again, you can welcome to do this in the chart. If that's helpful, I think it is. And then you run your first derivative test and find out this is decreasing, this will be increasing, and this will also be increasing here. First derivative is greater than 0 for both of these. And so something interesting is happening here, but right here you've located a minimum, and that's going to be at positive 1 comma negative 27. So again, to find this x-intercepts, sometimes the math gets a little bit hard. You have to set this function equal to 0 and maybe do, I don't know, synthetic division seemed to work pretty good for the first time. You could just factor out an x to see if it would factor by grouping. I think this one might. If you pull out a x squared here, leaving me with x minus 12, and then pull out, no, that doesn't work. So you'd have to do some long division here again. Eventually this will turn out to be x minus 4 quantity cubed. So go ahead and do synthetic division by this guy by 4. I don't know if you want me to do that again. You grab the coefficients, 1, negative 12, 48, and negative 64, and look for a 0. Bring down the first term, multiply, add, multiply, add, and that's probably 60. That did not work. Okay, I see that I did not bring down the first term correctly. Let me back this up. I should, geez, okay, rushing. So sorry. So I should have brought down this 1, bring down the first term, and then multiply. So that's a 4. This is a 1. So this is 8. So sorry. Negative 8, negative 32, 16, and there it is, 64 gives me a 0. Oh, I've struggled, I guess. So if this was an x cubed, this was an x squared minus 8x plus 16. Set that equal to 0, and by the way, I think that factors some more. X minus 4, x minus 4. So that's what gives me all of those 4's cubed. Why do this? Because then you have zeros. You have a 0 here and a triple root, 3, 4 right here. And what happens at a triple root? Remember, the original function is next to the fourth, so my ending behaviors are here and here, but a triple root does a twist, and then it's going to pass. I kind of missed, but it would pass through here. So a triple root does a twist, or to the fifth, or an odd root. So go ahead and finish up by finding the second derivative, setting this equal to 0, and finding the critical values, and then filling in a chart. You can see it's done here for you. You can go to Blackboard, print off the worksheet, and work through that and see if you don't get it. I wanted to work through, and then you, of course, you could use your calculator to kind of check for intervals in increase and decrease. So some of these get a little bit harder when you start finding the derivative, and some of us are still struggling on how to do low d high minus high d low. So again, I'm making things a little bit more complicated as we go along here. So I'll show you a quotient rule. Here's the low, the derivative of the high, minus high, and d low. Well, the d low is just a 1, so the high is just this. And you can set times 1 if you want. All over low squared. I would go ahead and probably just multiply out. So FOIL this over here. So 2x squared minus 2x minus 4x is minus 6x plus 4 minus x squared plus 2x minus 4. So I'm going to get an x squared term here and here minus 4x. That worked out pretty good, and I can say I'll factor out an x from that. So that's x minus 4 over, of course this is squared, I forgot it, x minus 2 quantity squared. So here's the first derivative in a fairly good form that I think you know, before you found that, I mean, I like this form because I would set it equal to 0, so I can see critical values are going to be 0 and 4. But before you found the second derivative, I would probably put this back into x squared minus 4x form, because that would be a little bit easier to do the second derivative. But it's still terrible. Low d high minus high d low. Oof. So chain rule, the derivative of the outside, write down the inside times the derivative of the inside, which is a 1. Decrease the exponent by 1. So all over low squared. So you can see these get complicated fast. So on this particular case, I think it's easier to factor out. I mean, you can multiply out if you want, but I think it gets easier to try to practice some factoring skills. So if you factor out an x minus 2, that'll leave me with 2x squared minus 8x plus 8 minus 2x squared plus 8x, and some things will cancel. And I'm just left with, and I've got an x minus 2 to the 4th. One of those will cancel. So I'm left with this 8 up top over x minus 2 cubed. So that turned out pretty nice. The critical value here is 2, but 2 is not even in the domain. What do I mean by not in the domain? Well, if you go back to the original function, way back up here, you can see 2, you can't let x be 2. So you got a vertical asymptote there. So again, these are potential points of inflection, but this one isn't a point of inflection. You can see that you have a vertical asymptote there. So there's no inflection here, no points of inflection. And we would have to go run our test with 0 and 4 to place them into the chart. And again, I would go from maybe negative infinity to 0, look at 0, and then 0 to 2, and then look at 2, and then 2 to 4, look at that interval, and then look at that 4, and then 4 to infinity, and then fill in the chart accordingly. You can see they've given you a couple hints here if you should be on target. When all said and done, this is what it should look like. And remember, this point 0, negative 2 will correspond to a maximum, and we've got a vertical asymptote here. That's why there's no point of inflection. And this 4, 6 corresponds to a minimum. And then you could graph the function. You can see there's an oblique asymptote there if you do some long division as well. There's 2 more examples, example 4 and example 5. And again, I would strongly recommend you to practice your derivative. Go ahead and pause the video here, see if you can't find the first derivative. I'll give you the answer for it, and then if you can't get this for the first derivative and work it out, then shoot me an email. The second derivative for this would be negative 20, 3x squared plus 4 over x squared minus 4. So go ahead and find the critical values, cubed. Go ahead and find the critical values from that and plug this in. Here's some worked out solutions, at least for the first derivative. But I don't think I worked out the second derivative. I just wrote it for you. So if you need to see this worked out, please do. Fill in this chart again. It should look like this when you get done. And then with this, hopefully you can sketch something. The idea is if I took your calculator away, which I'm not going to, you could still be able to graph something like this. So if the degree is something simple, you should know if it's just y equals 5, it's a horizontal line. If it's y is equal to mx plus b, it's a line. If it's a parabola, it's in this shape. And if it's a cubic function, it's an S. But what about fractional exponents? Well, that makes things a little bit harder. Again, practice finding the derivative of this thing would be, again, pause the video here and see if you can't find the derivative. You'd probably want to keep it in this form. You could rewrite that first derivative. I wouldn't, for the sake of finding the second derivative. but I would rewrite this. If you put this in factored form, it gets really easy to find the critical values. So sometimes I'm factoring this thing, because this makes it really easy to set equal to 0. I can see critical values coming up here. But then I would probably go back to this form to go ahead and find the second derivative. So again, I'm switching from a non-factored form to a factored form, because if it's factored, it's really easy to find critical values. If it's not factored, it's a little bit harder. So the second derivative here, work through it and see if you don't get this. The video is getting a little bit long, but if you need help getting this answer, again, shoot me an email. This is posted on Blackboard, so you can see some worked out solutions for this. Fill in this chart. You should get this when all said and done, and the graph will look something like this. I hope this video was helpful. Email me with your questions.